Hello, my name is Gabriel Werr and I'm ESR 8 of the 15 early-stage researchers as part of the European Organ-on-Chip Consortium. I work at Uppsala University under the supervision of Professor Maria Tenje, and I want to introduce you to my PhD project, Microfluidic Methods for Bead-based Assays on Chip. With the bead-based assays, we want to detect cytokine concentrations. Cytokines are proteins that regulate the growth and the differentiation of cells. They also play a role during immune reactions and inflammation of tissue, and can therefore be used to detect and monitor these processes. We work in close collaboration with ESR 7, my colleague Lisette in Bern, who is working with a lung-on-chip model. Here you can see a sketch from her model that mimics lung alveoli. The cytokines produced by the cells in her chip are diffusing into the cell media, which in turn can be pumped into our chip. Now, to detect the cytokines, we have microbeads in our chip that are coated in antibodies. The antibodies are designed to attach to the cytokines that Lisette is interested in to monitor the behavior of her lung-on-chip model. This method allows to concentrate the cytokines around the beads, which then can be labeled again with antibodies, this time attached to a fluorescent marker. The concentrated and fluorescent labeled cytokines can now be detected, for example, with a microscope. In order to hold the beads for the assay in place, we are using acoustic trapping. This technique allows to exert a force onto particles in a fluid as soon as a standing acoustic wave is built up in the channel. In the animation, you can see the particles being pushed to the node of a standing acoustic wave. We will use this to hold our beads against the sample flow. In the prototype design, you can already see the beads collecting in the trapping chamber, where a standing acoustic wave is resonating. The video is showing fluorescent light from the beads and the channel outlines as a sketch in yellow. After holding the beads for a while, the acoustic wave is turned off and the beads are flushed out of the system. The chip is etched in silicon and closed with a glass cover. These materials are very efficient in transporting the acoustic wave needed for the acoustic trapping. Here you can see the silicon wafer after etching. Based on this system, the process of inserting single beads into the chamber and exposing them to the cytokines will be automated, and the detection method for the fluorescent signal developed. With the ability to insert, trap, and release beads, the chip will be able to measure cytokine concentrations in regular intervals, giving more insight into the behavior of the cells during experiments. Since the antibodies attached to the beads can be changed, the chip will be able to detect several different cytokines without changing the underlying design of the chip. Towards the end of the project, the chip will also be connected to Marder's gut-on-chip model in Luxembourg and several other models at Fraunhofer Institute. This project is funded by the European Union's Horizon 2020 Research and Innovation Programme. For more information on the other projects, please watch the videos of my colleagues, especially Lisette ESR number 7 and Marder's ESR number 12, who are directly collaborating with me.